Hello and welcome to the DSpace Innovation Coffee Break. My name is Christopher Wiegand and I would like to present you some exciting new features for our sensor simulation environment. So environmental sensors are the eyes, are the ears of automated vehicles. With radar, camera and LiDAR sensors, the entire environment is observed and must be understood by the entire AD software stack. And here we see a lot of complexity. We see a complexity in terms of the AD software stack. We see the complexity in terms of the entire environment. And from my perspective, the key to develop autonomous or functions for autonomous driving and ADAS is simulations. There are other means, but simulation is the key to perform the validation. And when it comes to validation and simulation, there's always a question about the models, because only with the right models you can perform the right and correct tests. And here, sensor simulation or physics-based sensor simulation plays an important role. Being able to simulate all the physics within the environment, starting from material properties, going to wave propagation within the entire environment, or to specific sensor effects, which all have to be simulated within this environment, meaning rolling shutter, for instance, or lens effects. You have to be able to simulate ghost targets. And with our solution, you can develop and test your algorithms for autonomous driving and ADAS very efficiently. Let us assume you want to develop a radar algorithm. So you are responsible that the most significant information is extracted, that the most important information is identified by your algorithms, meaning you have to find the most significant detections within your data. How to do that? And here we have several means. We can use measurements. This is one possibility, of course. But most importantly, I think, is the simulation. You have more degrees of freedom, and with our solution, you have the means to parameterize your entire radar model completely, and additionally, you are able to create or to generate raw data in a very reliable way. Additionally, our solution can be run in hardware-in-the-loop and software-in-the-loop environments, meaning you are able to develop and test your algorithm with or without the ECU by using the same model. Before we dive into the application, let's have a closer look on the demo setup. This is the demo setup. Very simple. Our sensor realistic simulation is running on this standard PC, equipped with a high-performance NVIDIA GPU. And on this GPU, our sensor models for radar, LiDAR, and camera are calculated. And this is how it looks like. This is our sensor realistic simulation environment. And what we now want to do is to equip this vehicle with a radar. We only have to select the car, then we have to use the shortcut Alt-R, and now we have to position the sensor. This can be done by using those colored arrows, and you see it's quite convenient. And now the radar is positioned, but at the moment we use our standard or default model for radar, but we want to inject raw data into your algorithm. How to do that? We have to select the sensor, and then we have to select the right configuration file. So here we choose config raw data, open this file, and we are done. Now we change the view so that we can conveniently follow the ego vehicle. And now let's start the simulation. So the simulation is running, and now or at least I would like to show you that the radar sensor is providing raw data. By pressing the Alt-K shortcut, you can see our composite window, and this picture is the generated raw data. And now we want to use this data, or we want to feed this data into your device under test. For this, I use RTMaps as my development environment. I only want to enable the raw data generation example. Let's see. It is already enabled. I assume it should work. Now let's run the simulation. And here you see the range velocity plot, or the range Doppler plot. And by using the raw data, this range Doppler plot is calculated by performing some filterings and 2D FFT. This is the raw data part. But what if you need a target list, or you need a detection list? At that point, we have to change the model. So now let's switch to SRS again. Let's close the composite window. And maybe also let's stop the simulation. Now we only have to change the configuration file. We can select radar sensor config detection list. And now we are able to generate a detection list. We can start the simulation again. So the simulation is running. Now let's have a short look on the composite window. So the data generated by our model. So you see there's not so much data sent to the device under test. And now switch to RTMaps. And here we now have to disable the raw data example, and we can now enable the detection list example. And start. And now you can see all the detections here within RTMaps. You see, this is a very simple procedure in setting up the sensor simulation environment and to modify or exchange the radar model. Now let's have a closer look on the LiDAR sensor. Let us assume you want to develop LiDAR algorithms, and a Velodyne VLP16 is already selected. So with our simulation environment, it is possible to modify, to parameterize everything, and to implement such models. Additionally, you can also implement the protocol for this LiDAR sensor as well. But wouldn't it be more convenient for you to just use already existing models within our simulation environment? And thanks to our partnership with Velodyne, our sensor realistic simulation environments already provides a set of Velodyne sensors. For instance, the VLP16 or VLP32. And maybe now I can show you how to integrate those models and maybe how to visualize the data provided by our sensor realistic simulation. Similar to what I've shown to you with respect to the radar sensor some minutes ago, we now have to integrate a LiDAR sensor. For this, we have to select the Ego vehicle, and now we have to press the shortcut Alt-L, and we have to position the sensor. So, let me see. And I guess now it is positioned, but we have to select the right model. As I've mentioned, maybe the VLP16 or maybe the VLP32 is selected, or maybe another model. At the moment we have several models within our library. Let's select the VLP16 for now, and the configuration is done. So this LiDAR sensor behaves, or this model of a LiDAR sensor behaves like the VLP16 with a scanning pattern and additionally also with respect to the sensor protocol. Let's start the simulation. Maybe change the view. And now we want to visualize the point cloud. But to show you that this is a real VLP16, I will use the Velodyne software VeloView for visualizing the point cloud. For this, I already opened this VeloView software, and here it's only necessary to select the right sensor stream, and here you can see that the simulation and what is visualized in VeloView is very similar. So this is all what I wanted to say. And if you have any questions, if you think you need closer look on special features, you would like to have more insight into the topic sensor realistic simulation, then please feel free and contact us. And thanks a lot for your time and have a nice day.
DSpace, your partner in simulation and validation.